Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. It's Nano Days once again, and I have with me now Dr. Marilyn Minus, polymer engineer at Northeastern University. Hi, Dr. Minus. Thank you for joining me today.
Thank you for having me, Susan.
So first off, you're a polymer engineer. Let's talk a little bit about what a polymer even is and why they interest you.
Well, a polymer is basically a long chain molecule. So you can think of it like a bit like a pearl necklace, where each of the pearls represent a chemical group that's repeated over and over and over until it forms a chain. And typically you have about 100,000 to 1,000,000 pearls on a typical polymer chain. And so these really long molecules, they act like worms or snakes or any kind of spaghetti, any kind of long thing you can think of. And I'm very interested in them because they're so long and because they wiggle around so much, there's so many things you can do with them.
You said in the talk you gave a little while ago that they were kind of like worms, almost more so than spaghetti, because they're almost alive. They're actually moving while they're together. They don't just stay put in a messy glob.
Yep, exactly. So like worms, they wiggle past each other in a motion that we call Brownian motion. And so they're constantly moving around and wiggling, and then that allows them to slide around each other. And in some cases, that'll cause them to tangle up or unentangle. And so they're constantly moving a little bit. So that means the properties of every plastic material is changing just a little bit at a time. But it's something that you and I can't experience because that motion is so small compared to what we can feel as humans. And so just like worms in a bucket, that's how you can think about polymers in a plastic material.
Now, are polymers always all intertwined and sliding past each other? Or can you ever have a polymer that's either stationary or more kind of just lying by itself?
Well, most plastic materials, they will be entangled with one another, but there are regions where the polymer chains might lay next to each other, kind of like logs laying next to each other. Mm-hmm. And those regions are called crystals. The rest of the regions that are all entangled, we call it amorphous or random regions. But most polymers have a little bit of both. Pretty much every plastic material has a little bit of both of those in their structure.
And which kind are you interested in?
I'm interested in both structures, but I really want to make more crystal structures because the more I can align these chains and get them to straighten out, the stronger my properties of my polymers are going to be. And I'm really interested in producing strong materials.
So why can't you just lay a whole bunch next to each other and make strong materials?
Because it's a bucket of worms. And so getting all these worms to straighten out is a really big challenge because they don't really like to do that or want to do that. So that's the thing with polymers. Polymers prefer to be tangled up and they prefer to be jumbled up with each other. They don't really like laying straight. And so getting them to do that, we almost have to trick them into doing it or provide exactly the right conditions where they say, okay, this is the structure I prefer.
So how do you trick them?
We trick them by using different temperatures. And so the temperature at which you treat the polymers at can actually cause them to want to be in alignment with one another. Then you also have to put an additional force on them that'll actually push them in the direction you want them to align. And I do that by using flow.
Okay, so a couple things there. So the direction you want them to be, you want them to all be kind of parallel to each other. Is that the direction?
Because I make fibers, I want them to all be lined up and parallel with each other, but I want their strands to run along the length of my fiber. And so I'm aligning them in the direction of the fiber, but trying to get them all to line up. So I use temperature to get them to want to line up, and then I use flow to push them in the direction of the fiber.
So what do you mean by flow? Are you flowing water or a liquid over them?
I'm flowing a liquid, but it's a process that we use to make fibers, which is called spinning. And so spinning is a process that's typically done in some kind of solution. And if you can manipulate that solution by flowing it in a particular direction, then you can get all the polymer chains to flow in that direction as you make the fiber.
So I'm not sure if this is an accurate analogy, but is it like taking, if you've ever seen like spinning wool, you go to like an old Sturbridge Village type thing and you have a big clump of cotton or wool and you spin it and it thins it out? Is that a similar spinning or is it not?
Kind of. In those cases, that's what we would consider dry spinning, if you will, where you're taking all of these dry fibers and you're combing them all in the same direction. So you make a yarn actually out of those. And in that yarn, all of those fibers move along the same direction. direction. My polymer chain is kind of like those dry fibers, and I'm using liquid instead to flow them all in the same direction so that my fiber will eventually have all these polymer chains that are aligned. One thing that we do in our system is because polymers don't like necessarily being aligned all the time, they prefer to be more wiggled up or coiled, as we call it. We actually need to keep them aligned. And so we use in our research carbon nanotubes, which they prefer to be straight because they're rods, and we put them in there with the polymer, and for some reason the polymer likes to act like the nanotube once they're around each other. And so the polymer chains that can see the nanotube, or the ones that are really close to the nanotubes, they stay straight. The rest of the polymer chains might wiggle up, but as long as I can get some of those polymer chains, or the most of them, to line up in my fiber, that makes the properties go in the right direction, which is strong for us.
Okay, so you're working on making a stronger fiber, and you start with, you mentioned plastic and some of the fibers in the beginning. So you were talking about in your presentation, fibers, when we think of fibers, like a cloth, and we can just rip apart a piece of cloth. That's because in cloth, even though it looks fibrous, is it mostly still kind of jumbled up at that point?
Some of the polymer chains in the fibers of a textile are jumbled up, some are aligned. And so when you think of a jumbled up fiber, if you think about moving them, when you move a knot, for example, you're going to slide one fiber or one polymer across the other. So sliding doesn't take much energy. But once you pull that strand straight, in order to keep pulling it, you're eventually going to break it, and that actually takes more strength. And so if we add in the weak stuff, which is the sliding, and the pulling on it, that's stronger, you usually get a fiber that has an intermediate property. So textiles for us have intermediate properties, but I can rip one, so that's still relatively weak for a human.
So what kind of plastic has not even the intermediate properties? What's an example? So the textiles, that's an intermediate property. So I guess I went too far at first. What's the one with just a jumble of polymers?
So just a jumble of polymers would be slime, right?
Okay.
So the slime is very gooey and soft, and when you put it on a counter, it'll just spread out and flow almost. And that's something that's super soft, and all the polymer chains are jumbled up. And then we can move up from there to like a piece of saran wrap or a plastic bag that is easy to stretch, even a balloon. It's really easy to stretch. It's not as weak as the slime, but it's not as strong as, say, your shirt. And so it's easy to stretch and manipulate and so forth. And so then those fibers, that's kind of moving up in properties.
Okay. And then from there, you'd move into that intermediate property that has a few straight ones. That's kind of what we think of when we think of fiber textiles.
Exactly. Right. So you want to move into something that has a little bit of alignment and a lot of just tangled up stuff. So if we move away from everything being tangled up to more alignment, then the properties start to get better and better and better.
So what's the next step after textiles then?
After textiles is the super fibers, or the high performance fibers is another way that we talk about them. And these fibers have almost 80 to 90% of all the polymer chains aligned.
Oh, okay.
And so when we align more of the polymer chains, now you're pulling on the chain itself. Those fibers are really, really strong. And those are our bulletproof fibers and our fibers that we use in aircraft and spacecraft and cars.
So you said that these fibers are only maybe 80 or 90% aligned. Do we have something that's 100% aligned? And what would that be?
We don't have anything that's fully aligned. That's the dream. And so if we can make a fully aligned fiber where every single polymer chain is aligned, the properties of it is something we can't imagine. So I didn't say the properties earlier, but our textile fiber is like really intermediate, 0.5 gigapascals. So I can rip that. Our ballistic fiber, our bulletproof fiber is 5 gigapascals. I can't even cut that. But a fiber that has 100% alignment, it's 10 to 20 gigapascals. You don't even have anything on Earth that is that strong. So we have no idea what it would be like to work with that material.
Or how would you even test something like that?
Exactly. We don't even know if our machines might test it. The machine might break trying to test it. I don't know, because we haven't made it yet, but it would really be cool to try to achieve something like that.
And would that just be more optimization of the temperature and of the flow process? Or is there another trick you can add to it?
Well, those are the two ingredients that you need. But the challenges for us as researchers is we have to get all of the worms or all of the spaghetti strands to unentangle. And no matter how much you're dealing with, in every plastic material, you're dealing with billions of worms at a time. So not every single worm will unentangle. And so that's the trick. And if anybody going to do it, I don't know. Even getting to 99% might be really cool, but we'll see. We'll keep working at it.
So we talked a little bit about the plastics. We went from, slime to textiles. There's other types of polymers, though, aside from what we were just discussing. Can what you're doing be applied, or would you even want to apply it to other types of polymers?
Yeah, definitely. So out of all the polymers that we typically use today, like polyethylene, polypropylene, nylon, PET, or polyester, a lot of those polymers are very much wiggly chains, just like the polyvinyl alcohol or the slime polymer. And so what we're trying to do is take the recipe that we've learned from the polyvinyl alcohol or slime by adding nanotubes in it and making it straight to make that superfiber, and seeing if we could come up with a universal recipe that we can then use with all of these other polymers. So in my lab, we're working with polypropylene, polyethylene, nylon, polyester, polyacrylonitrile, or acrylic as most of us know it. So we're working with all of them to try to make a universal recipe. And the reason that's important is each polymer chain, the chemicals that make that chain are a little bit different. So while they're all long chain polymers, because they have different chemistry, you have to tune the flow and the temperature just right for each and every one. And so we're trying to develop a universal process so that we can make basically strong fibers from pretty much any flexible polymer chain.
Cool. Would it make all these polymers stronger? Like, regardless of the type of material you're using, just lining them up in straight lines, does that make them all stronger? Or is this a case where you still don't know what might happen depending on if you line them up or not?
Well, we know it from polymer research. We know that if you pull on the polymer chain, lining it up, then it automatically is stronger than if it was sliding next to each other. So it's always the case that aligned chains are stronger than tangled chains. But how strong that polymer is will depend on its chemistry. So not every polymer is going to be super strong, but most polymers are made of carbon, and carbon is that carbon-carbon bond, the same bond that makes nanotubes, is a very strong bond. So carbon-carbon backbone chains are the chains that will be the strongest materials, but other polymer chains out there can be stronger than they currently are, but they may not be the strongest.
That's so cool. I like the idea of focusing on the carbon and those strongest materials, and to see almost as a goal, can you break that machine that tests the strength on it, and see how strong you can really make something. Well, I want to thank you, Dr. Minus, for joining me here today and talking about the relationship between slime and really super strong materials.
Thank you for having me.
That's it for this week's show, but be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/CST or email us at podcast@mos.org. Thanks for listening.